Every night I'm trying so hard to get to bed, but my jets and tiny particles are scattered all over my head.
So just the other day, a friend was telling me, oh, it's so annoying. My students can't stop haranguing me about the mysteries of this particle/diffusion paradox and how it is that a bunch of scattering random particles can mysteriously exhibit diffusion-like behavior. You know who said that? No one ever. There is no particle diffusion paradox. It's not a thing. I just made it up. The relationship between random walks and diffusion is a fairly straightforward one. First, you learn about coin flips and Bernoulli distributions, then random walks, then Pascal's triangle, then the Gaussian, and then the heat or diffusion equation. If you know what those terms mean, then you probably know the drill. There are still strange and puzzling things along the way, Buffon's needle problem, that square root of 2 pi, but the connection to particles and random walks is not that hard to understand. By the end of this series, I want you to be able to say the same thing about the so-called particle-wave paradox, at which point we can leave the mystification out of it and focus on the many other fascinating aspects of wave phenomena. To get started, let's summarize what was said in the last lecture. Consider any collection of random walk particles that are heat-like, in the sense that the distribution of their random walk endpoints, when shifted so that all the paths start at the origin, has a distribution that converges to the kernel of the heat equation in the continuum limit. Or, if you don't know what that means, let's just say the distribution obeys the heat equation. That collection can be transformed into a wave-like collection of particles, the distribution of which converges to the appropriate kernel of the wave equation, or equivalently, the distribution obeys the wave equation. The transformation is as follows. 1. The particles are all endowed with a positive or negative sign, and the distribution or density in question refers to a net count of particles. 2. At each step of any random walk, an incoming particle creates a particle-antiparticle pair, such that the member of the pair that has the opposite sign of the incoming particle takes a step that is the reverse of the one the incoming particle just took, while the other one chooses a random direction for its successive step, just like the incoming particle will. All newly created particles will subsequently follow the same dynamics, and any random choices that these particles make will be statistically independent of one another. Also, since we'll typically do this on a lattice or grid, we'll also stipulate that particles traveling from the same point in the same direction that are of opposite sign will annihilate. Let's call this type of behavior Brownian-Huygens propagation. Schematically, wave propagation equals B plus B minus H, where the negative H designates a particle that initially executes a reverse direction step with respect to the incoming particle, whereas the other two execute their next step in random Brownian fashion. So let's prove that. I resolved to do this without calculus, and to help make that happen, I'll start with random walks on a square lattice of n dimensions, though in visualizing what I'm saying, I'll generally stick with 2 dimensions. In that case, the heat equation and wave equation are as follows. The only substantive difference between the two is that the time derivative is first order for the heat equation and second order for the wave equation. In taking a closer look, let's be extra diligent and remind ourselves that the Laplacian operator is a spatial second derivative, or spatial curvature, which is, up to a constant, equal to the difference between the average value of a function f over the nearest neighbors of some point x and the value of f at x itself. It's a measure of how well, in terms of f, x is keeping up with the Joneses. The same is true of the second derivative of f in time at any instant. The second derivative, or curvature, in time is twice the difference between the average of f just before and just after the instant and the value of f right then. So, first derivative, just the slope of f at x, no problem. Second derivative, just crank that out again and shift that to make it more symmetrical. So there it is, explicitly, the difference between the average of f in that neighborhood around x and f at x. So in the case of the heat equation, curvature in space determines the rate of change of f at any moment. If, say, the elevation follows the heat equation, and x is the location of a little valley, so that the curvature there is positive, then the elevation in the next instant will increase. If x is the location of a little hill, the elevation will go down. The heat equation is about evening and smoothing things out. And if that's not what you see when you try and simulate it, it might mean your system is numerically unstable and you need to rescale things so that the constant is smaller. In the case of the wave equation, the curvature in space is equal to the curvature in time. If the function is a sine wave and x is at a local minimum, we know that the function is bottoming out in time as well. More generally, if the curvature is some large number, say it's 1,000, and the function just a little while ago is the same as what it is now, we know that in order to satisfy the wave equation, in the next instant, you'll need to shoot up by 2,000 divided by the speed of light. So that alone gives you an indication that the wave equation is more dynamic than the heat equation. But any time we see that Laplacian or a second derivative of any sort, we should think about it in terms of neighborhood averages and whatever coordinate system that is chosen to suit the problem at hand. In Euclidean coordinates, the average is over the surface of an infinitesimal box surrounding the point in question. In spherical coordinates, it's in a little shell surrounding the point. In cylindrical coordinates, it's a ring, and so forth. And don't limit yourself to Euclidean or continuous space, because Laplacians can be extended to graph theory and all sorts of abstract systems where a neighborhood of some kind is present, and where one can execute a random walk from any location by keeping track of where the neighboring locations are. Now, because we want to first look at particles executing simple random walks, it makes sense to start with a lattice of some sort. And in that case, epsilon, as we've been referring to it, will not be able to approach 0 in the way it usually does. It can only go as low as 1, or the nearest neighbor distance, and that makes the above equations much, much simpler. So let's write them out. And let's stipulate that all the coordinates on a square d-dimensional lattice are integers. And this is how derivatives are going to look. Note that even though psi is a function of many variables, we'll typically only write out the argument that is of interest to us. Again, we always want to choose a setup that makes things as easy as possible. And to that end, we're going to set c squared in the wave equation to 2 over n, where n is the number of nearest neighbors used to calculate the spatial neighborhood average. So that for a square lattice, this is just 1 over the number of dimensions. And yes, that does imply that the speed of the resultant waves in those configurations will indeed be the square root of 2 over n. The reason for doing this, apart from making things easier, which is reason enough, is that we anticipate an eventual move to random walks that always step somewhere at any time, so that if a random walk lands on x at some t, we can be assured that it will be at some nearest neighbor in the next time step, and never simply stay at x. And when we do that, the central term, psi of x and t, cancels on both sides of the wave equation, so one less term to deal with. And with that, the wave equation becomes a relationship between the function's average over the nearest spatial neighbors of any point, and the average over that point's nearest neighbors in time, as we discussed a short while ago. What happens at x itself simply drops out of the equation. Let me also just mention in passing that all this works for hexagonal lattices as well, both the ones that have 3 nearest neighbors or even the more tightly connected ones that have 6 nearest neighbors. Hexagonal lattices are useful as gateways into the world of non-square lattices, and I will occasionally make reference to them for that reason. If we want to choose constants that make the central term drop out of the heat equation, note that the time derivative in that case is only first order, and the factor of psi of x on the time derivative side of the equation is -1 instead of -2, as in the case of the wave equation, where there is a second order time derivative. And that factor of 2 mismatch will be plainly evident in what follows. And having done that, we're almost done. It's just plug and chug so as to see what happens at psi of t plus 1, given what's happening at psi of t, and also, in the case of the wave equation, the value of psi at t minus 1. However, we still need to specify boundary conditions. In the case of the wave equation, we will need to completely specify psi of x at 2 successive times. Whereas in the case of the heat equation, we only need to do that at 1 time. We could also specify psi of x at t equals 0, and also the first derivative of psi with respect to time at t equals 0, the so-called Karl-Neumann boundary conditions. But as you can see for yourself from our earlier definition of a first derivative on a lattice, that's equivalent to specifying psi at 2 successive times, so we'll stay with the first option. So what's going to be the optimal way to specify a function on a lattice at 2 successive times? Let's consider a family of basis functions that are pairs of Dirac delta functions. The first member of the pair being a delta function peaked at x at time t equals 0, and the second is the delta function peaked at some nearest neighbor of x at t equals 1. And when I say peaked at x, I mean it has a value of 1 at x and is 0 everywhere else. If we're going to deal with particle steps or walks, that's about as obvious a choice as one could make. And we'll represent that basis function by a little arrow connecting those two nearest points. And even though there will be n of them coming out of, or going into any point, the obvious symmetry of the lattices we're presently dealing with means we only have to work out one example, and then translate and rotate it to all the remaining basis functions, one for every remaining arc. We can do this for the heat equation too, though being first order in time, it only cares about where the function is at t equals 1, not at t equals 0, so it only cares about the endpoint of that little arrow. Now some might say, hold on, if I have absolute freedom to specify anything at t equals 0 and t equals 1, then the peaks of those two delta functions should be able to be any distance apart. How will constraining ourselves to making the t equals 1 delta function be only one step away from the t equals 0 delta function allow us to fully specify the function? Well, observe that if I want my second delta function to be way over at some other point, I can express it as a sum of the following directed delta functions that are one lattice point apart. Or else this one. Or this one. Any path of interlocking nearest neighbor delta functions of the kind we just specified, we'll call that a seam, will do, as long as the subsequent point has the same red square black square parity as the first. And as you'll see, that's exactly what we want. The interlocking delta functions just so happen to cancel each other out at the intervening points in such a way that the particle or the delta function seems to jump a number of steps in one time interval. But note that even though the interlocking amplitudes along the seam cancel out, the momentum in this seam all points in the direction of the path leading from x to that distant target point along the path. So to the extent the delta function at the origin at t equals 0 represents a particle, the seam is like a series of momentum kicks that create the illusion of pushing that particle to some arbitrary location at t equals 1, like some infinitely fast conveyor belt or bullet train. This is another example of something that we can see in a discrete implementation more easily than we can with one in Euclidean space. I can even put together a chain of interlocking seams at time 0 and time 1 so that my resultant function is a delta function at t equals 0 and also t equals 3 as opposed to t equals 0 and t equals 1. I can go on to chain those in space and time so as to make very pretty interlocking lacework arrangements that give me any set of boundary conditions at t equals 0 and t equals z that I want, subject to the parity considerations I noted earlier. In other words, a series of kicks that create the illusion of a particle zipping forward and back in space-time so as to eventually wind up at time z at some arbitrary other location. Is this a practical approach for time travel? No, of course not. Even if you had a little Maxwell's demon ready and willing to set up boundary conditions in just the right way, this approach would not be remotely practical. But the infinite tape on a Turing machine isn't practical either, and that doesn't invalidate studying them. And the calculations required to set up seams that do what I'm describing are a worthy topic of study in and of itself, with lots of pretty segues into graph theory and topology. But we've got enough on our plate, so we'll let someone else have fun with that. So, to repeat, subject to some trivial parity constraints, and the fact that we're limiting ourselves to basis functions whose integral at any time is constant, so that we're implicitly excluding any trivial solutions which are of no interest to us anyway, the single-step basis functions described here are more than adequate to specify whatever we might need for our boundary conditions. In fact, since many paths of seams will work for any two desired endpoints, our basis functions are overcomplete for dimensionality greater than 1. They're kind of like a set of basis functions in phase space, though the momentum portion is a minimally thin dimension of up or down. An earlier paper also referred to these step-distant delta functions as hododic solutions, after a Greek word for path. And as students of Euler-Lagrange and Hamiltonian mechanics know, extending our coordinate space into a phase space is the first step in transforming equations of motion that are second order in time into ones that are first order. And that's what happens here as well. Given the linearity of the wave equation, this approach will allow us to transform the n nearest neighbor incoming flows, and for square lattices n is 2 times the number of dimensions, into n outgoing flows. So the value of the function at the points at any time is just the sum of the incoming or outgoing flows there. And as we'll again prove in a minute, they happen to be the same. But having taken care of the boundary conditions, let's start calculating. In particular, for any of those basis functions, let's look at the nearest neighbor points of the peak of the t equals 1 delta function, which, given our equations, are the only ones that have a chance of being non-zero at t equals 2. Using the wave equation that we simplified earlier, we can see that the value at t equals 2 at all the nearest neighbors of the endpoint of this basis function's little arrow is just 2 over n, which I once again emphasize to you is just the speed of light squared, with one exception, and that is the point at which our little basis function arrow originated at t equals 0, and the value there is -1 plus 2 over n. So here we see the coefficients introduced at the end of the first video. In fact, by considering all the basis functions whose arrows terminate at the same point in time, we have the following matrix equation, which we are about to see will transform any incoming flows into outgoing flows. So all the matrix elements are 2 over n, except for the diagonal elements, which are all -1 plus 2 over n. Note that with respect to those diagonal coefficients, the outgoing flow they refer to is always in the reverse direction of the incoming flow. If we do the same analysis for the heat equation, we see that in that case all the coefficients for that matrix are identical, with a value not of 2 over n, but rather 1 over n. No directionality there whatsoever, in keeping with our earlier observation that the heat equation only cares about where a basis function's arrow terminates, not on the directionality of that arrow. It is also easy to prove that the wave matrix is orthogonal. To see that, let's first look at the matrix for the heat equation again. Let's call it heat matrix. Apart from the fact that all its rows and columns each add up to 1, it seems pretty uninteresting and even boring. But it does have a curious property in that multiplying it by itself leaves it unchanged. In other words, the matrix is idempotent. That makes sense from what we said earlier about how the heat equation describes a process of evening things out, and the heat matrix is just n identical columns of coefficients that are already perfectly evened out. It's basically a heat death situation, and if we try and even out heat death, we just get back more heat death. If we have a randomly shuffled deck of cards and we shuffle it, we get a randomly shuffled deck of cards. Also note that wave matrix equals -1 times I plus 2 times heat matrix, where I is just the n by n identity matrix. Given what you know of the identity matrix and the fact that the sum of the rows and columns of heat matrix each add up to 1, you can easily see from the equation that the same is true for the rows and columns of wave matrix. Therefore, the square of this symmetric wave matrix is equal to the identity matrix squared minus 4 times the heat matrix plus 4 times the square of this idempotent heat matrix, so the last two terms cancel and we are left with the identity. In other words, the sum of the flows and sum of the squares of the flows for any combination of basis functions whose arrows point to any single point at any given time equals the sum and sum of the squares of the outgoing flows. And therefore it holds true for any solution of the wave equation which can be written as a sum of these basis functions. And that being the case, since we've figured out how incoming basis functions are transformed into outgoing basis functions, we can then repeat this transformation at all subsequent times, or if we're dealing with flows, at all subsequent time intervals. And all this follows directly from the equations of motion. The basis functions that were chosen just allowed us to conveniently separate the amplitude into distinct flows and easily calculate the matrix coefficients. Also note this works just fine for any positive integer value of n greater than or equal to 1. Why 1? Well, a lattice where the number of nearest neighbors is 0 or some negative number isn't much to go on, whether we regard n as the number of nearest neighbors or the number of columns in a transformation matrix. But any other n, We can make that work. Even non-integer values will work if n is some composite number of nearest neighbors. And if tomorrow some crystallographers manage to peer through a black hole and observe some universe where there seems to be some curious sevenfold symmetry in their spacetime, then without stopping to question what exactly that means, we can just construct a 7x7 matrix and verify that with regard to the heat equation or wave equation, there are no issues. And as long as the n little arrow vectors implied by those incoming or outgoing flows add up to 0 at any lattice point, we know that the implied momentum at any point is conserved too. Because all those factors of 2 over n that are present in any column are equally distributed in all those respective vector directions and therefore cancel out. And the only remaining contribution is the -1 that multiplies the outgoing direction that is opposite to the direction of the associated incoming basis function. So again, we have a direction reversal and a sign flip, ensuring that the momentum is conserved too. So that's basically it as far as the square lattice is concerned, given that the coefficients derived here are precisely the ones mentioned in the last video that led us to the particle implementation in question. In other words, Brownian-Huygens propagation, where a Brownian particle produces a particle-antiparticle pair at every time step. We can show that if we start with a particle distribution that equals some solution of the wave equation at any 2 successive time steps, that's particularly easy for a wave function defined via the basis functions we have chosen, we can use induction to show that the resultant distribution in any successive step will still have an expected value equal to the wave equation at that step. In other words, we were able to transform a heat-like set of random walk particles into one that is wave-like. We'll consider more general lattices below, but first, let's recapitulate what we just did. I'm hoping for many of you listening who are already familiar with numerical computation of partial differential equations on a lattice, the brief recap will be enough to give you what you need to catch up with what we've done so far. 1. We presented in standard difference equation form the heat and wave equations on a square lattice whose time and space coordinates are integers, and where any point has n nearest neighbors. We furthermore set the constants in both equations so that the central term, the value of the function at x and t itself, cancels on both the left-hand side and the right-hand side of both equations, so that they become relations exclusively among the nearest neighbors, both spatial and temporal, of any lattice point at any time. That cancellation implicitly divides our lattice into 2 locally disconnected sublattices, even parity, odd parity, red checker square, black checker square, so that a function that is non-zero only on one sublattice at a given time step will only be non-zero on the other in the next time step. And because the heat equation is first order in time and the wave equation is second order, the respective constants needed to cancel out the central term differ by a factor of 2. 2. To specify boundary conditions, we chose a set of basis functions consisting of pairs of discrete delta functions at 2 successive times, whose peaks are separated by 1 lattice length. And we showed that for dimensionality greater than 1, they are overcomplete, subject to those parity constraints I just mentioned, and restricting ourselves to the space of non-trivial solutions of the wave and heat equations. These basis functions map directly onto the vector arcs that at any time step connect a given appropriate parity lattice point to some nearest neighbor point in the subsequent time step, and they allow us to decompose wave amplitudes defined on lattice points at specific times to sums of incoming or outgoing amplitudes or flows along vector arcs during some time interval between 2 successive times. These basis functions, these incoming or outgoing vector arcs, constitute, in effect, a discrete phase space, though the momentum dimensions are very, very thin. 3. By applying our equations of motion to the basis functions, and keeping in mind that the equations only reference nearest neighbors of a single lattice point, we were able, in the case of the wave equation, to calculate the coefficients of the linear transformation that takes incoming flows at some lattice point and produces outgoing flows from that same point. We can do the same for the heat equation as well, though since it is first order in time, its output for the basis functions we are using depends only on where a basis function's arrow terminates. The matrix for the heat equation, call it heat matrix, is then, and this comes directly by way of the discrete equations of motion we started with, simply 1 over n times the n by n ones matrix, where the ones matrix is the matrix whose coefficients are all 1, whereas wave matrix is just -1 times the n by n identity matrix plus 2 times the heat matrix, the factor of 2 being a direct consequence of the aforementioned first order versus second order discrepancy between the constants used to cancel the respective central terms in both the heat and wave equations. Note, as mentioned numerous times, the positive 2 over n that appears in every coefficient of wave matrix is precisely what we chose the square of the speed of light to be in order to get those central terms to cancel. 4. Now, since heat matrix is easily proven to be idempotent, so that multiplying it by itself leaves it unchanged, it is likewise easy to see that wave matrix is orthogonal. Therefore, for any combination of basis functions, in other words, any non-trivial solution of the wave equation, the sum of the flow amplitudes and the sum of the squares of the flow amplitudes are conserved. Also, the momentum of the implied flows is conserved, given that the vectors associated with either the incoming or outgoing arcs of any lattice point cancel, so that the only surviving momentum term in wave matrix comes from the -1 factor multiplying the identity matrix. But since the respective directions of incoming and outgoing arcs are reversed, the negation and the direction reversal preserves the momentum as discussed in the earlier video. And those coefficients of wave matrix, as already discussed, are precisely the ones needed to justify the so-called Brownian-Huygens particle implementation described in the earlier video, whereby a particle creates a particle-antiparticle pair at every time step. That holds true for the case of the square lattice and can be similarly shown to hold for any regular lattice. And we'll generalize those results to other random walks in just a few minutes. But first, let's briefly note one other advantage of this approach that will prove useful if the particles we use have some other set of properties in addition to possessing a plus or minus sign. Say something like spin or charm or strangeness or charge. To that end, consider what happens if the lattice has multiple arcs leading from one lattice point to another nearest neighbor. For example, something like this. Here we see 4 nearest neighbors, but 12 arcs leading to those nearest neighbors, and we can make that number as high as we like. Conveniently enough, when you plug in the appropriate numbers for this more finely reticulated network, it turns out that the sum of the flows on any multiple arcs leading to the same nearest neighbor gives us the same amplitude contribution that is obtained from the single arc case. Therefore, not only is the sum and squared sum of the flows on the multiplied arcs conserved, because the matrix relationships we derived do not depend on multiplicity, the sum and squared sum of what we get when we consolidate the multiplied arcs is also conserved, as is the momentum. So that's pretty nice, especially since you can easily see it holds in the general case. I'll leave it to you to do the simple algebra needed to verify this. So if the particles have some distinguishing property, and we don't want a negative and positive particle to annihilate unless those properties are the same, or else, if we want, for reasons to be elaborated later, to impose a Pauli exclusion principle on this lattice that takes into account those distinguishing properties, we can easily do that with this multiple arc approach. So up till now, the focus has been primarily on square lattices in any number of dimensions. Can the results shown here be generalized to other random walks that satisfy the heat equation? Let's go for it. Some of you might say, given the conservation properties these random walk particles can be made to obey, that it's perhaps possible to construct an infinitesimal cube around any cluster of paths, take into account the particles leaving and entering, and show the wave equation holds that way. Let me throw some cold water on that approach by considering an ideal Newtonian gas. Note that the particles there are all conserved, as is the sum of their momenta, and the sum of their kinetic energies, or the square of their momenta. If that threefold conservation were all that was necessary, we could prove the density of an ideal gas also satisfies the wave equation. Except it doesn't. Ideal gases do indeed support sound waves, but they dissipate rapidly and are not useful when it comes to generating the kinds of wave phenomena not susceptible to rapid heat death. So that's unlikely to work. Even though the heat and wave equations may sometimes seem ubiquitous, they're not in any sense inevitable, and lots of obstacles stand in the way of their implementation. For example, consider a distribution of 2 types of particles, each of which is provably wave-like, except that one propagates on a very fine lattice, the other on a coarser one. Will their summed or superimposed distributions follow the wave equation? No, of course not. If their speed of light differs, then a pulse created at any point will produce 2 wave fronts, each traveling with a different speed. What about a smoother sum of particles with varying speeds? No, that will just produce some smeared out wavefront. That's no good either. I suppose it's possible that the different wavefronts might cancel out in some way to produce a composite wave. But without anything to back that up, it's just wishful thinking. How about with the heat equation? Would two types of particles, each walking on different lattices, at least give us the heat equation? No, they wouldn't, for similar reasons. The distribution of paths at a given time, all propagating from some initial pulse, would be an average of two Gaussian kernels. And an average of two Gaussians is in general not Gaussian. But one thing that Gaussians have going for them is the central limit theorem. Consider the distributions obtained by a particle taking a large number of steps, call it m, from some more general distribution of directions and lattice lengths. The central limit theorem tells us that that distribution of the sum of m steps will indeed be Gaussian for a wide variety of single-step distributions, and that distribution of a large sum of m steps can be well approximated by a discrete random walk on a square lattice, which, as the earlier discussion showed, can indeed be modified into a Brownian-Huygens distribution having some composite speed of light. That's already a very useful result and demonstrates why even if the underlying random walks are on some crazier lattice, they can be approximated using the simpler square lattices considered thus far. But at best, this seems like something that could be turned into a weaker form of the main theorem, and really doesn't give us anything new, given that the difference equations on a square lattice we started with can already be applied to any situation for which the heat equation holds. It's not bad for a start, but the strong form of the main argument states that that same large variety of random walk distributions can be modified directly without having to posit some intermediary proxy square lattice, and that's what we really want, but it remains to be proven. It's worth noting that in 3 dimensions, the most often studied propagator for the continuous wave equation, the one where the time derivative is initially 0 everywhere, produces a wavefront in spherical coordinates with a radial profile that is itself a delta function. In other words, a limiting case of a narrow Gaussian. So there, we can again look to the central limit theorem to try and prove our claim for at least that. So do a Taylor series expansion around the wavefront and see what terms predominate. In other words, back up that earlier wishful thinking about different wavefronts canceling out with something more substantive. We'll do a variation of that approach when we tackle the Klein-Gordon equation. But that's only in 3 dimensions. Other dimensions are a lot weirder. In 5 dimensions, the radial wavefront is the derivative of a delta function, and in 7 dimensions, it is the second derivative, and so on. In even dimensions, the derivatives are of half order, which is something that only makes sense when considering the Fourier frequency space. But as for the d-dimensional propagator of the heat equation, that's just a plain Gaussian in any dimension. So if we want a simpler approach to deal with not only that continuous case multidimensional wave menagerie, but also a crazier variety of discrete walks and lattices, then maybe it's best to base our approach on something that generalizes easily, like the d-dimensional Gaussian. And how crazy a variety are we talking about? Well, while I favor lattices, it's worth noting that we don't really need a lattice for any of this. Earlier, I mentioned the 7-fold space-time symmetry what-if scenario, as if it was something too weird to have any meaning, but really, there isn't much to it. A particle, let's say it's in a 2-dimensional Euclidean space, can simply choose to take a step in one of 7 directions, each separated from the previous step by some integer factor of 2 pi over 7. And that's fine. We can start with the 7 by 7 matrix setup and reverse our analysis to show that it satisfies the wave equation in the case of a 7-point spatial neighborhood of any point that is used to calculate the Laplacian. True, it means the endpoints are no longer guaranteed to coincide, so we have to hypothesize some rules about how close particles have to be before they can annihilate and so forth, and that makes things messier than they need to be for now. And that's why I prefer grids, even as we'll see random ones, because even the simple notion of dividing a circle into 7 equal sectors is something I myself would find difficult in any circumstance, especially given Gauss's proof on constructing regular polygons. And a theory that requires fundamental particles to be smarter than human beings probably isn't going to simplify anything either. But 7-fold symmetry is not crazy enough, I say. Let's let n, the number of neighbors, vary at every point. Let's let the steps to those nearest neighbors be different lengths and random directions when embedded into a d-dimensional space, as long as the resultant distribution of paths and particles is heat-like. There are still other generalizations we could make. We could make n increase with time, for example, though it cannot decrease unless we start over in a sense. But let's hold off on that for now. Variable numbers of neighbors with random directions and steps are more than enough craziness for a start. So what we're assuming is that at every moment, the distribution of particle paths starting from the origin is such that a normalized count of all possible paths leading to some small arbitrary region around the point xp at time t, where t is some integer, equals the propagator of the heat equation that has that nice and well understood Gaussian shape in any number of dimensions, unlike the weird wave equation propagators. We could also combine the count of paths and the normalization constant by assigning a weight to each path, so that we could just sum those directly if that's easier. We'll go with the former option just to make what follows a little easier to write and read, but keep it in the back of your mind. And you may ask yourself, does it have to be all possible paths? Can't it just be some? I'm going to say yes, it has to be all possible paths, so that if I construct any path from the origin at time 0 to xp at time t via any sequence of nearest neighbors, I know it has to be present in that distribution. That will be important. Also note that the relationship between the path's endpoint density and the Gaussian kernel holds not just at xp and t, but everywhere, at least in the continuum limit. In particular, it holds for xp and t minus 2, xp and t minus 4, and so on. And you might say, well, that's oddly specific, and I'd agree with you. And let's also say this relationship holds for the nearest neighbors of the origin, where any of the paths might be at t equals 1, just for good measure. We're not going to use induction here, but someone else might at some point, so let's leave the door open for that. Likewise, it's important to note, since we're dealing with branching processes in the case of Brownian-Huygens propagation, that we're going to normalize by scenario. Conceptually, we'll start a particle in the exact same place and restart the clock at a very, very large number of times. Ideally, a number many times larger than the total number of possible paths. And then count up the signed or unsigned particles that make it to xp at time t, and then divide that result by the number of scenarios. The number of possible paths will of course increase as we progress to lattices with a larger number of nearest neighbors at any point, and it also increases with the duration of any path. But the normalization constant in what follows does not depend on that or any lattice or random walk parameters. Now, allowing n to vary over different lattice points inevitably leads to some confusion. You might well ask, given that we're considering all possible paths, don't the points with more neighbors create more paths, and shouldn't that be reflected in our sum over paths? Yes to both questions, and if n for a given point is twice as large as it is at some other point, then the first point will indeed create twice as many paths, but those paths are only half as likely to be encountered in any scenario. The moment that a question of the form isn't the fact that n varies from point to point going to complicate the weighting pops into your head, remember what I've just told you. Tie a string around your finger or something. How do we verify that when we transform a set of paths of random walks into a Brownian-Huygens set of paths by giving the particles and path signs and making the incoming particle emitted particle, antiparticle, etc., etc.? That's a huge mouthful that I'm getting really tired of repeating. So let me say any random walk distribution that has been transformed in this way has been undulated. So how do we prove that when some heat-like set of paths has been undulated into a much larger set, that the result satisfies the wave equation? Note that the assumption that the heat equation is satisfied everywhere tells us several things implicitly. The Laplacian exists throughout this random lattice because how else could one verify that the heat equation is being obeyed? We know that there's a well-defined dimension for the space in question, the one implied by the d-dimensional Gaussian kernel that the distribution mimics everywhere and at any time in the continuum limit. The space is smooth or isotropic if we expand out far enough to where the lattice steps are unobservably small. Everything is rotationally invariant about any point, just like that rotationally invariant d-dimensional Gaussian kernel. That too comes to us by way of assumption, so it doesn't require proof either. The k factor in the associated heat equation, which in effect fixes the scaling between space and time, is a constant throughout the space these walks explore, despite being a composite of the individually varying k's along a given random walk. And those individually varying k's are everywhere equal to 1/2 of the local speed of light squared in the corresponding local discrete wave equation. And both the k's and the c squareds depend solely on the number of nearest neighbors at each point, just like the Laplacian itself. So the composite speed of light squared parameter in the wave equation, which is just twice the k factor in our heat equation for any of those n's we looked at, will likewise be a constant. Both constants are properties of the medium and do not depend on whether the time derivative in the equation is first order or second order, so that what holds for the heat equation holds for the wave equation, because the geometry of the lattice is the same for both. Or are we already implicitly assuming the wave equation must be satisfied if the heat equation is? I'd better back off that one and mark it as unproven. So let's return to the notion that in both the case of the heat-like distribution of random walks and whatever we get when we undulate that into Brownian-Huygens propagation, we're essentially counting some totality of paths. Every path that is in the undulated version has a doppelganger, call it a Brownian shadow, over in the starting set of heat-like paths, though if we assume that the Brownian shadow paths all begin at the origin at t equals 0, then we also need, in the case of the wave paths, to specify something at t equals -1 or t equals 1. Let's go with the first option and set the amplitude to 1 at t equals -1 for one of the nearest neighbors of the origin, knowing we'll have to repeat what we're about to do for the other neighbors as well. Even though Brownian-Huygens is a branching process, every resultant particle or path has an ancestry tree that unambiguously defines a member in that heat-like distribution. But there are going to be many wave paths that have the same Brownian shadow, given that there are 3 outgoing particles per incoming particle at every step. And depending on how many sign-flipping Huygens backpropagation steps there were along the way, there is a sign factor to consider as well. But it would really be nice, and really it would be all I needed, if I could convince you that the undulated distribution obtained from that heat-like distribution of paths was just some combination of those heat-like paths, or equivalently some combination of values of the heat equation, multiplied by constants that had nothing to do with how crazy or asymmetrical or variable the random walks were. If that were the case, then given that we already have an example of heat-like paths that obey the wave equation after being undulated, in other words, the square lattice case we just considered, then that would be all I needed, because if the weights don't depend on the structure of the lattice, it would mean any heat-like distribution could be turned into a wave-like distribution. That would be really nice. Let's call that the number 1 wish. Specifically, the ability to prove that the wave-like paths are some combination of heat-like paths without regard to the peculiarities of a given step. By assumption, we can state that regardless of how crazy those random walks get, everything works out fine for the heat equation. But given all the prolific particle creation and also annihilation that happens when we undulate those paths, it's also hypothetically possible that even if the heat-like paths come together properly, because they're all the same sign, the undulated paths might still turn into self-canceling mush without the uniformity we have in the case of the square lattice. With that in mind, consider again that distribution of walks, weighted or else unweighted with an overall normalization constant, such that the sum of paths that wind up at xp at t gives us the kernel for the heat equation. Let's call that sum heat paths of x and p and t, or better yet, since xp is the only point of interest right now, let's just call that sum heat paths of t. Just how much bigger is the number of paths arriving at xp at time t over the undulated set of paths, in other words, wave paths of t, given that at every step in Brownian-Huygens propagation, 3 outgoing particles are generated for every incoming particle. The total number of wave paths without regard to destination is 3 to the t times the comparable number of heat paths, but that multiplier doesn't hold when comparing only those paths that make it to xp at time t. Note that there's additional structure in the path steps of any member of wave paths of t than what we find in members of heat paths of t itself, given that everything in the latter distribution is unsigned. For example, every undulated path step can be either Brownian or Huygens. The latter can happen only on a reversal step and must involve a sign change, but note that a reversal step can also itself be Brownian. Moreover, any Brownian step can be either a step corresponding to the incoming particle or random walk continuing its path, or else a newly created particle, whereas the other newly created particle is by necessity a Huygens direction reversing and sign negating step. So in terms of multiplicity and sign, every wave path, in addition to its well-defined Brownian shadow, needs a character string to fully specify it, with the possible characters being either b or h, and has a multiplicity and sign factor equal to 2 to the g Brownian times -1 to the g Huygens, and reflects the fact that I'm adamantly insisting throughout this lecture that n always refers to a count of neighbors, so I'm definitely not going to call it n Huygens. And g Brownian is likewise simply the number of b's in a paths string. Given that each of these wave paths has an implicit earlier starter step leading from the same nearest neighbor to the origin at t equals 0, let's agree to prefix each of those strings with the special starter character s to make that explicit. But since it is the same for every single member in our set of paths, it does not affect the weighting, at least not yet. And given the form of this multiplicity and sign factor, let's agree to group all the contributions to the wave amplitude by way of these BH strings. To see how this will work, let's first consider the subset of wave paths of t which have 0 h's, paths of particles that never once took a backpropagation sign flip step. Again, that doesn't mean that there are no reversals, because not every reversal has to be Huygens, but it does mean there are no sign flips. Every member of that subset has a Brownian shadow in heat paths. And as stated earlier, heat paths of t contains every single possible path leading from the origin to xp at time t, and its count, when divided by a normalization constant that doesn't depend on the wave equation, is equal to the kernel of the heat equation. After all, that's just our starting assumption about how the particle paths are heat-like. Moreover, every member of heat paths of t is a Brownian shadow for some member of this 0h subset. And given that they all have the same multiplicity and sign factor, our number one wish is thereby fulfilled, at least for this subset. Maybe that's just beginner's luck, but that's a promising start. In particular, consider a simple case of a square-dimensional lattice where xp is t steps away from the origin along the direction of whatever starter step we chose. In that case, there is only a single path in heat paths of t, and so, for that point, the wave amplitude equals 2 to the t times the value of the heat equation there. But you might say, hold on, what if this is some hexagonal lattice or a crazier lattice in which a straight line path is impossible? Or what if we want to look at a square lattice case where xp is rotated 45 degrees away about some other axis? In that case, there are 0 paths starting at the origin and consisting of t steps, either for the heat or the wave equation. In answer, I'll admit that if discrepancies like those don't vanish when we take the continuum limit, it only means that the heat equation is not being satisfied to within whatever accuracy we initially said it was, and that means our starting assumptions were never met. So we're still good. But of course, there's more to wave paths of t than just that one exceptional subset. So let's keep going. What about a subset of wave paths of t which has exactly one Huygens step? Because I want you to always have in mind some specific string. Let's say the one we're interested in has an h as the 53rd character, assuming the path is 53 steps or larger, and all the remaining characters, except for the s starter step, are b's. But since what we're about to say will be pretty much the same for any of the remaining possible strings with one h, we'll just designate this subset as being single h. But please remember, we're referring to one specific string, not the subset obtained by considering all such single h strings, because that's the way in which we're going to count things up. Also note that the path we just considered for the square lattice, the one that is t steps away at time t in the direction implied by the starter step, is not in this or any other single h subset, because that straight line path has no reversal steps, which means it cannot contain any Huygens step either. By the way, if you happen to think of a counterexample having to do with some specific single h string that violates any of the assumptions I'm about to make, I'll ask you to set it aside until I'm completely done. If we look at a graph of our path, that Huygens step looks like a little thorn or spike sticking out of the path. Though since it consists of 2 back and forth steps, maybe a blade is a better metaphor since that has 2 sides. No, let's stick with thorns since they're sticking out from some larger path. Let's snip off that 2-sided Huygens thorn for every path of this one Huygens thorn subset. We thereby create a subset of steps of length t minus 2 that have no Huygens backpropagation sign flip steps, leaving alone any remaining reversal steps that, by assumption, do not contain a Huygens step, since we're considering paths where there was only one to begin with. And as we learned from the 0 Huygens step subset we just looked at, those are very easy to deal with. It is true that getting rid of that single Huygens step will mean introducing a factor of -1, since any Huygens step involves a sign flip, and the multiplicity will also drop by 2, since we also got rid of a Brownian step along with the Huygens step when we snipped off that 2-sided thorn. In other words, the associated string lost both a b and an h. Notice that the resultant snipped path has a Brownian shadow in the set heat paths of t minus 2, because we already said that our overall distribution consists of all possible paths. So if the path made it to xp and has 2 fewer steps, it therefore has to be present in heat paths of t-2. Moreover, we were also assured, in an oddly specific way, that heat paths of t-2 also equals the kernel of the heat equation at t-2. The multiplicity and sign factor is now different, down by a factor of -2, but the value it is multiplying doesn't depend on the craziness of the paths in any way, and is just equal to the heat equation kernel, which you can derive with no lattice or random walk at all. But some of you will say, wait, hasn't it already been made clear earlier that the number of strings with a single h for a given xp and t is indeed lattice dependent? Isn't that already evident from the specific example given of the straight line square lattice path extending t steps in the direction of the starter step, which gives us a different path count than does the hexagonal lattice? No, what has just been demonstrated here is that the number of strings with a single h for a given xp and t depends only on the total number of paths, forgetting about b's and h's altogether, at t-2, which according to the assumption is equal to the propagator at t-2 up to some error term or discrepancy that must go to 0 in the continuum limit if the paths in question are heat-like. And the multiplier of that term is not lattice dependent either. So at least for the subset of paths with 0 or 1 Huygens backpropagation sign flip steps, all of which have strings with 0 or 1 h's, our number one wish is fulfilled. Next, let's consider the subset of paths with just 2 Huygens steps. But in that case, I see a problem. There are 2 ways of creating paths with 2 Huygens steps. Those reversal steps can follow one right after the other, or they can be separate. Dethorning in the first case means getting rid of one HH snippet, and in the second case getting rid of 2 separate BH snippets. But in the latter case, the fact that we are trimming away 2 B's along with 2 H's means there's a difference in the multiplicity and sign factor than the one we get by trimming one HH snippet. But look, as long as we dethorn each of those cases separately and assigned weights appropriately, we're still good. And since we're doing all the enumerating and weighting string by string, we're already doing that. The resultant paths will have lengths either of t-2 for those paths in which the 2 Huygens steps follow in succession, or else t-4 for those paths where there's an intervening Brownian step. The end results in both cases are paths that have no Huygens steps. So we're still good. This is still just a mix of weights multiplying values of the heat equation at earlier times, both of which have nothing to do with the distribution. But what about 3 Huygens steps? In that case, the Huygens steps can be all crammed next to one another, or there can be 2 crammed together and 1 somewhere else, or else 3 steps all separated by 1 or more Brownian steps. But even then, as long as we adjust the multiplicity sign factor by 2 for every lost B and -1 for every lost H character in the associated strings, our number one wish remains intact. It's definitely a lot of careful weighting, which we already knew, but we're more interested in what isn't there, specifically a lack of any explicit dependence on lattice particulars beyond whatever is needed to make the Brownian shadow paths heat-like. I think most of you have long since figured out where this is going, and since removing a thorn shaves off 2 steps, we'll need to go at most t/2 repeats of this. Are we done? Not quite. Something still isn't right here, and I'm guessing some of you have already picked up on it. Remember how I've repeatedly told you that the heat equation is first order in time, and the path steps that the walks associated with it take at any moment are chosen without regard to directionality. So how can it be that something as directional as a wave pulse, with its backward propagating Huygens step or wavelet, can be a combination of solutions of the heat equation at the same point xp? The answer is, it can't. In fact, there are certain paths containing thorns whose snipping away requires some additional elaboration. In particular, what about the ones whose first step beginning at t=0 is a Huygens step? Or more precisely, whose first steps are any odd number of Huygens steps? Call that the odd initial h category of paths. And we need to figure out how to deal with those. Paths that start with an even number of h's can be dethorned just like the rest we have already considered. But dethorning those beginning with an odd number of Huygens steps means multiplying by a factor of -1 and also removing the very first step prior to t=0, which, as specified earlier, means the defining step that began at that nearest neighbor at t equals -1, so that after snipping away that step and the initial Huygens backpropagation step, we're left with paths that start at the nearest neighbor of the origin at t equals 1, the very same nearest neighbor where the wave paths all began. And that's just the heat equation propagator beginning at that neighbor of x of 0 at t equals 1. So one step away, minus sign. In effect, this takes care of that first derivative in time and space, and that adds the directionality we need. Also, if we wind up snipping away a string until there's nothing left, in other words, a string consisting only of the starter step plus an odd number of h's, we'll assign that a weight of 1, since on a discrete lattice, that is the initial value of both our heat equation and wave equation prior to any steps having been taken. That means that when we multiply that path by -1 to account for the odd Huygens step, that contribution is exactly what we need to recover our equations of motion. Let's check that out. At t equals 1, the only paths at any other neighbors of x0 than the one where the wave paths started have the two-character string SB associated with them, where S stands for that initial starter step as mentioned earlier, and each has a weight of 2 to the 1 equals 2. In other words, twice the number of paths than what we get when considering the path counts of the heat equation at that point in time. In other words, yet again, 2 over n is twice 1 over n, the latter being the heat equation at that nearest neighbor point at t equals 1. And as for the remaining nearest neighbor where the wave paths started, that leads to two possible two-character strings, namely sh and sb. The multiplicity sign weighting for sh resolves to -1, based on the rule we just stipulated for the odd initial h category of paths which after dethorning become empty strings. And the corresponding weighting for the sb string resolves to the weighting for the wave paths that lead to the remaining nearest neighbors. In other words, -1 plus 2 over n. So there's our wave matrix again. That means if you don't believe the multiplicity and sign factor I simply presented to you earlier, you can derive it for yourself using induction and what was just stated. In fact, you can use induction to prove the whole theorem. So now we're done. But some of you are probably still asking, is that all there really is? Okay, we got that first derivative added in, but what about all that backpropagation and direction reversing that was so carefully laid out in the last video? Where's the sum of the squares of the flows, or the sum of the momenta that are both conserved on average? Not to mention the absolutely conserved sum of the amplitudes. Why was that number one wish all that we needed in order to prove this? So let's break down how this went. We came up with a way of expressing the wave equation in terms of the heat equation at some specific time t and at earlier times, which is completely independent of the peculiarities of the lattice structure, apart from the absolute requirement that every path step can be followed by its reverse. How do we know that the result of that complicated expression obtained by dethorning our paths equals the wave equation? Because we know that when the craziness is taken away from our lattice, and we repeat all that in the case of a regular square d-dimensional lattice, the result is the wave equation. So that fixes the actual value of that expression for at least one system of paths that we likewise know is heat-like. That's very important. All we did just now was prove that the values that come from the undulated paths are not dependent on how crazy a lattice we're using or whether we're using a lattice at all. The weirdness doesn't matter as long as it preserves the heat equation. In other words, as long as the distribution of paths at any time is heat-like. But knowing the value doesn't change still doesn't allow us to know what that value in the case of the undulated paths actually is. And so I'm implicitly relying on our earlier work with the square lattice to give us that, and to tell us that the expected net particle count of the undulated lattice paths on a square lattice is in fact the wave equation in the continuum limit. I hope that's clear. Even if it turns out that I've made some error regarding the weights, which is possible, or else if we want to apply this to some different set of paths with some different counting rules, say using Fermi-Dirac statistics, all that is fine as long as the new weights that determine the multiplicity and sign of the undulated paths relative to their respective Brownian shadows depend only on the duration of the path and the number of backpropagation sign flip steps. Before discussing Dirac and Feynman's path integral approach, let's test out what was just derived using the one-dimensional case of Pascal's triangle, which is just a count of paths for a one-dimensional heat equation, and for which the wavefront, in the case of the wave equation, consists of 1s along a specific outside rim of that triangle and 0 everywhere else, with the non-zero rim being determined by the initial conditions. For example, for t equals 4, where the Pascal's triangle is 1, 4, 6, 4, and 1, there are 2 to the 4th equals 16 wave paths. No Huygens steps at all for the path that gives us the wavefront clearly, so that one is just a string of 4 b's, and the heat equation is 1 over 16, so the product is 1. So that checks out. Let's just go through the rest of this visually. But do note that even though the heat equation is an even function about the origin, the asymmetry needed to create that single non-zero wavefront value manifests itself even in the different number of strings that lead to non-zero values for a given endpoint. I'm guessing if you're a graph theorist or some other expert in combinatorics, then getting all those off-the-front values to vanish is not that big a deal. And it's probably some well-known recurrence relation or something that's trivially easy to obtain with the right moment-generating function. And certainly this is a lot more difficult than simply solving the wave equation itself in one dimension. But to me, as simple and obvious as the translating solutions of the one-dimensional wave equation are, it's still amazing how almost the entirety of Pascal's triangle collapses and folds away like that, especially given that the result is, unlike the Gaussian kernel used to express it, relativistically invariant, and I hope some of you will find it fascinating as well. I have one other second-hand observation to offer on this, and for some of you I think it might actually be more convincing than the proof itself. So I'll restate something I said early on in this series, but from a higher level. Two of the most fundamental concepts in mathematical physics are, 1, the Gaussian bell curve, the heat equation, Brownian motion. All of these are, at the core, a summation over all possible paths. This goes back to Gauss himself and Pascal's triangle, which dates back to at least the 11th century. 2, calculus of variations, the least action principle of classical mechanics, wave functions in quantum field theory, Fermat's principle. All of them involve functions or functionals over the set of all possible paths. In particular, Dirac's path integral formulation of quantum mechanics replaces the classical trajectory of a system with a sum over all possible paths, with each path weighted by a factor proportional to e to the is over h bar, where s is the path integral of a certain function, specifically the Lagrangian. If this is news to you, pause this video, type path integral formulation into a search engine, maybe put Dirac and Feynman in there, and see what you get. It's something everyone who knows what an integral even is should know about at some point. And the simple act of juxtaposing those two fundamental concepts should already be enough to indicate that there must be a fundamental relationship between Gaussians and waves, between the heat equation and the wave equations of quantum mechanics, including the classical wave equation we focused on. But some will say, yeah, but what about that exponential? What's that about? And I'll say all that means is that we're talking about propagation, which is just repeated stepwise multiplication. What is propagation? It is literally, at every time step or generation, a process of multiplication. That is how we get exponential growth. That is how we get cascades and bursts of most any kind. Be ye fruitful and multiply at each generation. But what about that imaginary factor? You can't tell me that isn't weird. And to that I say, all that imaginary factor means is that at every 2 steps or 2 generations, there's a factor of -1 that's introduced. And we've seen that from the very beginning. Whenever an equation is second order in time and we're solving for t plus epsilon, there's going to be a term involving t minus epsilon, 2 epsilons away, with a factor of -1. We've also seen that every Huygens reversal step takes us back to where the path was 2 time steps ago and includes a sign flip. In other words, a factor of -1. And when we dethorn a path, we leave it 2 steps shorter and take away a factor of -1, unless there are 2 Huygens steps in succession, but that's one of those exceptions that proves the rule. And the fundamental rationale for I is do this multiplicative operation 2 times in order to get -1. So it's no surprise we see it here, even with purely real, and in fact integer, counts. That's all implicit in the above proof, apart from the realization that the path integral is not dependent on the specifics of the lattice, but only to what portion of the path consists of backpropagation. It's also not immediately obvious that whatever is contained in that path integral is something that we can use the heat equation to infer. And hopefully those 2 additions in your mental toolkit were worth the time spent acquiring them. In any case, that means that whatever is powerful and useful about Gaussians, central limit theorem, law of large numbers, should apply to waves as well. If something is difficult to prove about waves or Lagrangians, remember that connection and see if using something like the central limit theorem or Gaussian functions can help you out of it. Anytime you see Brownian motion or Monte Carlo simulations or binomial trees, whatever, if it's a sum over all possible paths or scenarios, and if it can be negated in some way, admittedly that's a big if, then it can be turned into a wave. And that wave is not some flimsy little thing that falls apart into noise and self-cancellation at the first opportunity. No, it's hefty and robust like the central limit theorem and like Brownian motion. All roads lead to it because, in essence, all roads went into calculating it. That's enough about path integrals, given that people like Dirac and Feynman have already explained and elucidated that topic far better than I ever could. I'm hoping for at least some of you that will be the aha eureka moment that tells you, of course it works. When you put it like that, it's kind of obvious and probably something a dozen people have already discovered and then forgotten. Something you could probably work through yourself quicker than a homework set. So go ahead and do that. Take it to the next level. Write up a term paper or dissertation or article. Not a lot of things come along that are unexplored territory and that don't require large amounts of financial backing and high-tech machinery. So if you see something a little out of the way that requires nothing more than pencil and paper and some basic code, take advantage of it. Eventually, somebody will make this stick in the collective math-physics lexicon, and maybe you and I will have played a part in that. And with that, I'll mark this as done. Maybe for those of you who took or will later take a calculus of variations and learn about Lagrangians and quantum field theory, and who don't get asked, but probably should be. Hey, what other simpler formalism that we've all heard about includes a summation over all paths or scenarios, and therefore shouldn't there be something there we can exploit? Yes, there should be, and there is, and the next time you come across that connection, maybe the video here will click in your mind and it will lead you to something you can use. Before moving on to summarizing what will be in the final video, let's reflect on what has happened since the recap and what a wild ride it was. We went through wave-like random walks with sevenfold symmetry. We went through the weak form of the theorem that gave us a way to use walks on a simple square lattice to create wave-like paths in any crazy space, in the same way that a linear tangent allows us to get a grounding on whatever crazy curve we're trying to understand. All that by way of the central limit theorem. We went through ideal gases and why they aren't waves. We listed and were eventually able to tame an entire menagerie of the crazy wave fronts that are found in the continuous case, and that vary with each dimension, and instead prove what we needed by way of simple graph theory. Granted, the heat equation did most of the heavy lifting, but that's fine. The very fact that we were able to make that connection and use it to our advantage is something worth keeping in mind. So let's move on to what we'll see in the final video. It'll mostly be physics, but there's still a little bit of math related to implementation, and I'll give you a taste of that now. Let's return to our earlier diagram, the B plus B minus H schematic. Since the term in parentheses is a particle-antiparticle pair, whose contribution to the net particle count is 0, what if we generate several such pairs at a time instead of just one? Or how about if we generate such a pair only if a coin toss yields heads, but in that case generate 2 such pairs? Would that work? No, it would not. Because in both those alternatives, neither momentum nor the sum of the squares would be conserved, even as an expected value. That backflip direction reversal that keeps happening along every arc, Courant and Hilbert call the continuous case of this the Huygens reverberation, needs to persist until it is annihilated away and must retain all of the momentum transfer apart from self-canceling random noise. I know the notion of particle-antiparticle pair creation is an evocative one, and suggests Feynman diagrams or those photos from cloud chambers where a particle shoots by and hives off a particle-antiparticle pair. But none of that is Brownian-Huygens propagation, except maybe a quasi-classical limit of some underlying process much like that. Or maybe what happens when different instances of Brownian-Huygens propagation are coupled together. In Brownian-Huygens, as defined here, it is the backpropagation sign flip that all by itself takes care of the momentum transfer. But returning once again to our schematic, even though changing the parameters of that B minus H particle-antiparticle creation is a bad idea, what we can do is generate multiple particle-antiparticle pairs where both members of a pair are Brownian. In other words, they both choose their outgoing directions randomly. But if we go that route, we should arguably make it work in our favor. For example, in order to reduce the inherent noisiness in these kinds of branching processes. And we'll say more about that when we discuss variance reduction. In other words, preferentially canceling all the positive and negative particles generated at any lattice point in such a way as to still satisfy the output statistics given by the above-defined transfer matrix. And we'll also be able to use it to bring about regularization, as with Tikhonov ridge regression, which in this case means generating doubly Brownian particle-antiparticle pairs so as to reduce the overall particle number. Not the net particle number, which will be exactly conserved, but the total number of particles regardless of sign. Because in the absence of any such regularization, the overall particle number will keep growing, even as the net particle number stays constant. It's just that there will be an ever-increasing number of positive and negative particles whose difference is always a constant. That might not be important in a pure math sense, and a physicist specializing in the renormalization group might not care about it either, but it will understandably bother most everyone else, so that needs to be addressed. It's also worth noting that some people hearing about this for the first time might be disappointed that when we move to integer particles, instead of generating flows of real numbers, which means multiplying by factors of 2n at every time step, then the momentum and the square of the flows are only conserved in terms of the expected net numbers of particles at any point in time. But there's really no need to be upset. Even in standard quantum theory, there are brief violations of energy and momentum conservation. That's what quantum tunneling is, and students learn about that within their very first few lectures on quantum mechanics. Feel free to consider the properties that are conserved only on average in the same way. It's another kind of fluctuation, reflecting the fact that in any particle implementation, it is discreteness itself which must be conserved. And I'm going to ask everyone to apply the same consistency standards throughout the rest of the series, since I suspect you'll realize, upon closer inspection, that some of the problems or difficulties encountered in an approach like this are present in the standard theories as well, though in the latter case we've simply learned to accept them as they are, or else brush aside any problems or difficulties as more quantum tunneling. Also, in considering how an approach like this might be applicable to quantum mechanics, I'll show that the wave functions considered here produce an integer quantity that when integrated over some macroscopic spacetime path, in other words, when a measurement is taken by some macroscopic observer living within that lattice universe, will yield a non-negative number with a probability that can be made as close to 1 as we like, assuming our lattice length is small enough. What is that integer quantity? For now, I'll just point out that when anyone interested in keeping things simple sees a probability function of any kind that is equal to the product of two terms, and that also applies if we're talking about a single term that is squared, the first thought that will come to mind will be that this is some kind of joint probability, with the understanding that both of the individual events being sampled are statistically independent. And that's the approach we'll take. It's not going to give us anything much different than, say, the many worlds interpretation, or even the Wigner von Neumann interpretation, in which measurement occurs in the mind of the observer. Really, the only thing that might possibly change in an approach like this is that the microscopic dynamics will be simpler. But quantum mechanics on the macroscopic Schrödinger-Cat level will still be plenty weird. The fact that we're always going to be dealing with quasi-probability densities whose integration over any path is only non-negative in some macroscopic limit does mean we'll be able to get around Bell's inequality. But even so, this is not going to be a pilot wave theory or any single particle theory at all, given that Brownian-Huygens is fundamentally a branching process. If anything, the particles generated by any such process are more like fields than a single particle wave function. Single particle wave functions are, after all, a non-relativistic fiction anyway. It's certainly possible to have fields that conserve properties like charge, but charge is just the net particle number within a field, and this approach has no problem keeping that conserved. I'll also note that we can impose the Pauli exclusion principle, or PEP, in our lattice. But note that on occasion it will be violated. That happens in the real world as well, with particle fields that likewise respect the PEP, namely fermion fields, whenever the gravitational forces become enormous enough, or presumably even in the quiet vacuum, say two positron-electron pairs are created so close to one another that the positrons or the electrons are too tightly crammed to be able to satisfy the PEP, at least for a brief moment. In the case of the vacuum of free space, any microscopic fermion collapse can perhaps be brushed off as just another kind of quantum tunneling, but I'm not familiar with any specific research done on that. In any case, if one is bothered by the fact that it's not possible to always satisfy the PEP in these Brownian-Huygens processes, then even if that means this approach is worthless for fermions, and if so, well, that's how it goes, it's worth noting that the standard field theories might not pass that hurdle either. Finally, given the generalization of the result for random walks on square lattices to other more weirdly distributed random walks, we'll discuss how deformations in our not necessarily square lattice can cause our space to bulge and flatten out, and how this warping can be used to give us not just the kind of curved spacetimes encountered in general relativity, but also when the deformations are sparse and homogeneous enough so that they can be accounted for by way of a first-order perturbation, the Klein-Gordon equation. So that's what is left on our to-do list. But all that is extra credit or special problems, and regardless of what you make of that, it shouldn't obscure the primary purpose of this series, which is to show you the close relationship between random walks and the wave equation, and how to use the former to generate the latter. In closing, I'll gratefully remind you how much cool stuff there is in the science and math videos just a click or two away from this one. You can learn about Klein bottles, Sierpinski's carpets, elephant's toothpaste, Galois theory, etc. It's beautiful and impressive, but for the most part, it's established science. This, on the other hand, is new. Apart from some related dissertation work that didn't really allow for this kind of presentation or breadth, what I've presented here is still largely unexplored. In fact, much of what was in this last video was included only because of comments that viewers of the earlier video made, which made me realize that what I thought was obvious actually needed to be proven. So there's still a lot to do here, and I thank those viewers for their suggestions. But as for wave-particle duality, the primary remaining mystery about that is why close to none of you, according to my best guess, have ever heard about how to turn Brownian motion into waves before watching this series. And that is a mystery I cannot explain, but I would encourage you to tell your friends and colleagues about it, tell your students or teachers or thesis advisors. If you're a blogger or journalist or editor, consider using your soapbox to let other people know about this. And do please click the like button if this was something of interest. Thank you again for listening. I hope my own evident enthusiasm will be more contagious than off-putting, and I hope you will stick around for the final video.
Oh, they make them into cigarettes and coffee. I cannot get my fill. Oh, they mix them in the engine oil to make all the wheels go round. And they hide them in the armory, shoot the enemy missiles down.